A magnetic field is created by a charge in motion. Since a current-carrying wire consists of many moving charges, it creates a magnetic field in the region around the wire. The magnetic field acts in a circle around current-carrying wires. Magnetic field itself is a vector quantity and affects the magnetic force exerted on a moving charge near the wire. Since magnetic field is a vector, it's going to have both a magnitude and direction. The direction of the magnetic field is given by the right-hand rule. If you curl the fingers on your right hand and point your thumb in the direction of current in the wire, your fingers will curl in the direction of the magnetic field. If I look here, if I point my thumb in the direction of the current, my fingers would curl out of the page, above the wire, and then below the wire they would point into the paper. Now it's hard to draw on paper or on a screen a vector that goes into or out of the page. So the way to draw a vector out of the page to draw a circle, and then a vector into the page is represented by an X. So the direction of the magnetic field vector is given by the right-hand rule. The magnitude of the vector, or the magnetic field strength, is given by the variable B, which is measured in the unit teslas. The formula for it is mu sub 0 I over 2 pi r. Mu sub 0 is the vacuum permeability or magnetic permeability of free space, which basically represents space's ability to magnetize. It's 4 pi times 10 to the negative 10. I is the current running through the wire producing the magnetic field. And whenever you're finding field magnitude in physics, it has to be at some point in space. R is the distance from that point in space to the wire producing the magnetic field. Now I have two example problems looking at finding magnetic field direction and magnitude. Example A is just on finding direction, and it looks at two sets of current carrying wire and finding the net direction of the field due to each pair. Using the right-hand rule, these currents are to the right and to the left. If I point my thumb to the right, below the wire where point P is, my fingers are curling into the page. So I have a field into the page due to the top wire. Due to the bottom wire, I'm going to point my thumb to the left now, and my fingers in that region are going to curve into the page. So both wires at point P have fields into the page, so the net field on this one is also into the page. For the next one, the currents are going into the page and out of the page, and then point P is between them again. So for the left wire, if I point my thumb into the page, my fingers are going to curl clockwise. So I get a magnetic field here that's clockwise. For the other one, I'm going to point my thumb out of the page, and my fingers curl counterclockwise. If I look at point P, the left wire has a field doing this, the right wire has a field doing this, so at point P, the next field is down. The next problem I have here, example B, looks at finding the net magnetic field at this point here, P, due to two different wires, wire A, which is above it, and wire B, which is below it. Before I calculate magnitude, I want to figure out what the direction that the field due to each wire is. So for wire A, if you point your thumb in the direction of current to the right, and then you go below the wire and curl your fingers, they would go into the page. So the field due to A is into the page at P. Wire B has current going the same way, but now we're looking above the wire. So if I point my thumb to the right and curl my fingers above wire B, they would curl out of the page. So they have fields pointing in two different directions, so I'll find the magnitude and take the difference. For wire A, the distance is given as 0.1. So using the formula mu sub 0 I over 2 pi r, I get that it's 2 times 10 to the negative 7, or 2 microteslas into the page. For B, it's a distance of 0.3 away. So using mu sub 0 I over 2 pi r, I get 1.33 microteslas. A has a bigger field magnitude, so the net field's into the page. And when I calculate the difference, I get the net field is 0.67 microteslas into the page. A way to get a more concentrated magnetic field is to run a current carrying wire in a loop. So here, current through this loop would run clockwise. And I'm going to go around in a few places and use the right-hand rule. On the top left, if I point my thumb in the direction of current, my fingers would curl into the page. Top right, same thing. Fingers curl into the page on the bottom right, and into the page here. So everywhere along the loop creates a field into the page. So the magnetic field inside the loop is into the page everywhere in the loop. So a loop of wire creates a concentrated magnetic field that acts in one direction, and that field becomes stronger when you use more loops because each individual loop is producing a magnetic field. A coil of conducting wire with many loops is called a solenoid, and running current through a solenoid produces a magnetic field inside the solenoid. Here's a solenoid connected to a battery. The battery is going to send current this way through the solenoid, and that's going to create a magnetic field that looks like that inside the solenoid. Where inside the solenoid you get a strong concentrated field, and then outside the field is much weaker. This acts a bit like a bar magnet, where you have magnetic field going into one pole or one side of the solenoid and coming out of the other side of the solenoid. The direction of the magnetic field in the solenoid is given by another right-hand rule. For this right-hand rule, you curl your fingers in the direction of current, since now the current is going through many loops, and then your thumb will point in the direction of the magnetic field or magnetic north. The formula for the magnetic field in the solenoid is given by mu sub 0 Ni over L. Mu sub 0 is still magnetic permeability, N is the number of loops of wire, I is the current that's being passed through the solenoid, and then L is the length of the solenoid.